Let's look at 3 lines of code: loss.backward, optimizer.step, and optimizer.zeroGrad. These 3 lines train every neural network on Earth, from GPT-4 all the way down to your weekend side project. Sure, you can copy-paste them from Stack Overflow. They work. Your model trains. But what's really happening under the hood? I used to think PyTorch was this massive, incomprehensible beast. Turns out, I was wrong. Dead wrong. The entire system follows the same 5-step recipe. Not 50 steps. Not 500. Just 5. Today, we are going to implement these 5 steps using nothing but raw math and basic arrays. No magic, no abstractions. Just pure, transparent code. Then, and only then, we'll see why PyTorch's tools exist. Because once you've built the engine with your bare hands, the professional tools suddenly make perfect sense. And it all boils down to these 5 steps. Okay, look at this table. This is your cheat sheet. We are going to walk through this entire process together, step by step. Give me 1 hour. Just 1 hour. We'll build your understanding from the ground up. Welcome to Chapter 2. Today, we're talking about the only data structure you really need. Everything we do in PyTorch, every single thing, will be built on one single object. And that object is torch.tensor. Think of a tensor as the fundamental building block. It's the basic noun of the PyTorch language. Now, you might be thinking, hey, that sounds like a multidimensional array from NumPy. And you'd be right. But this one comes with superpowers. Our goal today is simple. We are going to master this one crucial object. So let's dive into the 3 common patterns for creating tensors. Get these down, and you're well on your way. Pattern number 1, direct creation from data. This is the most straightforward. You have a Python list, and you want a tensor. Simple. You just use torch.tensor. First, we'll import torch. Then we create a standard Python list called data. Let's say it's a list of lists with 1, 2, 3 in the first row and 4, 5, 6 in the second. Then we just call my_tensor equals torch.tensor and pass in our data. When we print my_tensor, look at this output. We get a beautiful tensor object that perfectly mirrors our list. Tensor. And inside, we see 2 rows, 1, 2, 3, and 4, 5, 6. Easy, right? Okay, on to pattern 2, creation from a desired shape. This one is huge. You'll use it all the time when you're initializing model weights. The idea is, you know the shape you need, but you don't know the values yet. So let's say our input is a shape tuple, maybe 2 rows and 3 columns. Let's look at the code. We define shape equals the tuple 2, 3. Then we can create a tensor of 1s, a tensor of 0s, or a random tensor using torch.randn with that shape. Now, let's print the random tensor. And here's what we see. A random tensor with 2 rows and 3 columns filled with random values. This is your model's starting point before it has learned anything. All right, pattern number 3, creation by mimicking another tensor. This is a clever one. Sometimes you need a new tensor with the exact same shape and type as another one. Instead of doing it manually, we can just mimic it. Let's say we have an input, a template tensor we created earlier. It has 2 rows, 1, 2, and 3, 4. Now, we can create a new tensor with the same properties using a function like torch.randn_like. We pass in our template, and we can even specify a new data type, like torch.float. So when we print both the template and the new randn_like tensor, Check it out. The template tensor is our original 1, 2, 3, 4. And the new randen_like tensor has the exact same shape, but it's filled with new random floating point numbers. Super useful. Okay, so we know how to make tensors, but what's actually inside a tensor? This brings us to shape, type, and device. Every tensor has 3 critical attributes. You will use these constantly for debugging. Let's create a tensor called, well, tensor, using torch.randen with a shape of 2 rows and 3 columns. Now let's print its shape, its data type, and its device. Here's what we get. The shape is torch.size with a list of 2, 3. The data type is torch.float32. And the device is CPU. Let's break these down. First, .shape. It's a tuple describing the dimensions. Listen to me. This is your #1 debugging tool. I'm serious. 90% of your errors in PyTorch will be shape mismatches. Master this. Next is .device. This tells you where the tensor lives. It's either the CPU or, for massive speedups, on CUDA, which means the GPU. And finally, .detail, the data type of the numbers. Did you notice the default was float32? This is not an accident. Why float32? Why not just integers? The answer is gradients. The entire engine of deep learning works by making tiny, continuous adjustments to a model's weights. We're talking about nudges. You can't nudge a parameter from the number 3 to 3.001 if your data type only allows whole numbers. It's impossible. And that tiny nudge, that's the entire game. So the rule is simple. Model parameters, your weights, your biases, they must be a float type. And float32 is the standard. Data that represents categories or counts like class labels? Sure, those can be integers. But the stuff that learns has to be a float. This is where PyTorch's core magic comes into play. It's a system called Autograd. That stands for automatic differentiation. It's PyTorch's built-in gradient calculator. And you activate this entire powerful system with one simple switch. The magic switch requires grad equals true. By default, a tensor is just data. To tell PyTorch it's a learnable parameter, you must set requires grad equals true. This is it. This is the most important setting in all of PyTorch. It sends a message to the Autograd engine. It says, this is a parameter. From now on, track every single operation that happens to it. Let's see this in action with data versus a parameter. Okay, look at this code. First, a standard data tensor. x_data equals torch.tensor with the values 1, 2, and 3, 4. Simple enough. Now for a parameter tensor, where we need gradients. We create w equals torch.tensor with values 1.0 and 2.0. And here's the key. We add, comma, requires grad equals true. So when we print the requires grad property for each of these, the output is exactly what you'd expect. The data tensor requires grad is false. The parameter tensor requires grad is true. Once you flip that switch to true, something incredible starts happening behind the scenes. PyTorch begins to build a computation graph. Think of it as a live recording of your operations. Let's walk through building the graph together, step by step. Our goal is to compute z equals x times y, where y equals a plus b. First, we need 3 parameter tensors. We create a equals torch.tensor of 2.0 with requires grad equals true. Then b equals torch.tensor of 3.0 with requires grad equals true. And finally, x, a tensor of 4.0 also with requires grad equals true. So far, we just have 3 separate tensors. Now, for the first operation. We defined y equals a plus b. Watch what happens. PyTorch instantly creates a new node in its graph. It connects a and b to an add operation, which then creates our new tensor y, which has a value of 5.0. Next, we perform the second operation, z equals x times y. And just like before, PyTorch adds to the graph. It connects our tensor x and our newly created tensor y to a multiply operation. This produces our final result, tensor z, with a value of 20.0. So, if we print the result z, we get 20.0. That's simple math. But the graph PyTorch built? That is the real story. So how can you prove this graph actually exists? Every tensor that's created by an operation has a special attribute. It's called .grad_fn. Think of it as a breadcrumb, pointing to the function that created it. Let's peek under the hood. We'll check the tensors we just made. First, let's print z.grad_fn. The proof is right there. It says it was created by a loss.backward 0 object. That's the multiplication. Next, let's print y.grad_fn. It points to an add backward 0 object. That was our addition. But what about a? Remember, a was created by the user, not by an operation. So when we print a.grad_fn ... the result is none. This is the tangible evidence of the computation graph. When we call loss.backward later on, PyTorch will walk this exact trail of breadcrumbs to calculate the gradients. Here's what that final graph looks like, with the grad_fn breadcrumbs included. You can see z points back to the multiply operation, and y points back to the add operation. It's a perfect map of our calculations. So far, we have the tensor. That's our noun. We have Autograd. That's the nervous system. Now, we need operations. We need the verbs of PyTorch. These are the actions, the calculations, the things our models will actually do. And here's the good news. The vast majority of deep learning is just a few simple operations, repeated over and over and over again. Our goal here is to master these core verbs, especially the ones that trip up beginners the most. Let's tackle the single most common beginner mistake, the classic confusion between the star operator and the @ symbol operator. First up, element-wise multiplication, which uses the star. This one is pretty straightforward. It multiplies matching positions. Think of it like laying 2 tensors on top of each other and just multiplying the numbers that line up. The key rule here is that the tensors must have the exact same shape. Let's look at an example. We have tensor A, which is a 2x2 tensor with values 1, 2, 3, and 4. And tensor B, another 2x2 tensor with values 10, 20, 30, and 40. When we type element-wise product equals A star B, what PyTorch calculates is this. In the top left, it's 1 times 10, top right, 2 times 20, bottom left, 3 times 30, and bottom right, 4 times 40. So the result is a tensor containing 10, 40, 90, and 160. Simple. Second, matrix multiplication, which uses the @ symbol. Now this is the one. This operation powers neural networks. The rule here comes straight from linear algebra. The number of columns in the first matrix must equal the number of rows in the second matrix. Let's see it in action. We have M1, which is a tensor with a shape of 2 by 3, and we have M2, a tensor with a shape of 3 by 2. See how the inner dimensions match? 3 columns in the first, 3 rows in the second. Perfect. So when we calculate matrix product equals M1 @ symbol M2, the resulting shape will be the outer dimensions, a 2 by 2 tensor. And the result is a tensor with values 58, 64, 139, and 154. So, to be crystal clear, when you build a linear layer, that classic formula y equals xw plus b, you will always use the AT operator. Always. Next up, reduction operations and the dim argument. A reduction is any operation that reduces a tensor to a smaller number of elements. Think of things like sum, mean, or maximum. Let's look at the default behavior. Imagine we have a tensor called scores with 2 rows and 3 columns. When we call scores.mean with no arguments, it calculates the mean of the entire tensor. It adds up all 6 numbers and divides by 6. The overall mean, in this case, is 15.0. Simple enough. But this is where it gets powerful. The dim argument lets you control which direction to collapse. For a lot of people, this is a huge aha moment. Here's the setup. Our scores tensor represents 2 students and their scores on 3 assignments. A simple rule for 2D tensors like this is dim equals 0 collapses the rows. It operates vertically. Dim equals 1 collapses the columns. It operates horizontally. Let's see the code. We have our same scores tensor. To get the average for each assignment, we need to collapse the students, so we collapse dimension 0. We write scores.mean with dim equals 0. To get the average for each student, we collapse the assignments, so we collapse dimension 1. That's scores.mean dim equals 1. And look at the results. The average per assignment gives us 3 values, 1 for each assignment. The average per student gives us 2 values, 1 for each student. Let's visualize this collapse with this table. Look at the scores table. We have student 1 and student 2 and their scores on 3 assignments. When we calculate mean with dim equals 1, we are collapsing horizontally. For student 1, we take 10 plus 20 plus 30, and the average is 20. For student 2, we take 5 plus 10 plus 15, and the average is 10. See? We got the average for each student. Now let's try the other way. When we calculate mean with dim equals 0, we are collapsing vertically. For assignment 1, we take 10 plus 5, and the average is 7.5. For assignment 2, 20 plus 10, average is 15. For assignment 3, 30 plus 15, average is 22.5. It's so powerful once you see it. Mastering the dim argument is non-negotiable. You will use it absolutely everywhere. Selecting your data. From basic to expert. Basic indexing works just like you'd expect from NumPy. It's for selecting uniform blocks of data. For example, we create a tensor X with values 0 through 11, reshaped into a 3x4 grid. If we want to get the third column, which is at index 2, we just write X, open brackets, colon, comma, 2. That means give me all rows, but only the column at index 2. And the result is a tensor with 2, 6, and 10. Easy. But let's get more dynamic. What about argmax? This function finds the index of the highest value. This is how you find a model's final prediction. Let's say we have a scores tensor with 2 rows representing 2 predictions. For the first row, the best score is 20, which is at index 3. For the second row, the best score is 30 at index 1. When we call torch.argmax on our scores with dim equals 1, it finds the index of the best score for each row. The result is a tensor with values 3 and 1. Perfect. Now for the expert level tool, torch.gather. Standard indexing is great. Get column 2 for all rows. But what if you need something more specific? What if you need from row 0, the element at column 2, and from row 1, the element at column 0, and from row 2, the element at column 3. A totally custom selection for each row. You could write a for loop, but that would be slow. Torch.gather does this in one highly optimized operation. Let's walk through it. First, we have our data tensor, a 3x4 grid. Now, we create our shopping list. It's a tensor called indices to select. It has the values 2, 0, and 3, each in its own row. This list tells Gather which column index to grab from each corresponding row in our data. So when we call torch.gather, we pass in our data, we tell it to gather along dim equals 1 because we're picking columns, and we pass in our index, which is our shopping list. And look at the selected values. Let's check its work. From row 0, it was told to get index 2. It went to row 0 and got the value 12. Correct. From row 1, it was told to get index 0. It went to row 1 and got the value 20. Correct. And from row 2, it needed index 3. It went to row 2 and got the value 33. Perfect. Mastering Gather unlocks advanced, dynamic model capabilities. It is a cornerstone of complex architectures. We are building a model from scratch, and this is part 1, the forward pass. This is step 1 of our 5-step loop. The whole point of this step is just making a guess. So what is a forward pass? Think of the forward pass as the model's first guess. When you first create a model, it knows absolutely nothing. So initially, its guess is completely random. And that's exactly what we want. It's a blank slate, ready to learn. Our goal for this section is simple. We're going to implement a model's first guess using only the raw tensor operations we've just learned. No fancy libraries helping us out just yet. So what's our model? We're starting with the most fundamental one, simple linear regression. You'll see this formula everywhere. Y hat equals xw plus b. Let's break that down. X is our input data. W is the weight, and B is the bias. And that little symbol, y hat, is our model's prediction, or its guess. Now, W and B are the two knobs our model can turn. Our entire goal, the whole point of this whole process, is to find the perfect values for them so our prediction, y hat, gets as close to the real y as possible. Time for the setup. Let's create our data. We'll make some fake data that follows a clear line. Y equals 2x plus 1, but with a little bit of noise. Let's walk through the code. First, n equals 10. That means our batch of data will have 10 data points. D underscore in equals 1 and D underscore out equals 1. This just means each data point has one input feature and one output value. Next, we create our input data x using torch.randen with n and d underscore in. Now for the important part. We create our true target labels, y true, by using the secret answers, the true w and true b. The true w is a tensor with 2.0, and the true b is 1.0. So we calculate y true n tensors by taking x at true w plus true b, and then we add a little random noise at the end. Now this is crucial. The model will never see true w or true b. Its entire job is to discover them just by looking at the input x and the correct answers y true. Next, we create the model's brain. These are the parameters w and b that it will actually learn. We initialize them with random values, and then we turn on the magic switch. Let's look at the code. We initialize our weight w using torch.randen with the right shape, and here it is, comma, requires grad equals true. We do the exact same thing for our bias B. A random number with requires complete equals true. Let's print them out and see what we get. The initial weight W is a tensor with some random value like 0.4137. And the initial bias B is something like 0.2882. This is the model's initial hypothesis. It's completely wrong, but that's okay. It's a start. And now for the implementation. The moment we translate our math into code. The math is y hat equals xw plus b. The code is y hat equals x at sign w plus b. That's it. That's the forward pass. So let's see our first guess. We run the forward pass through our model. Then we print the prediction y hat and the true labels y true to see what we got. The result is a disaster, just as we expected. Look at this. The prediction for y hat gives us values like 0.07, 0.18, and 0.14. But the true labels are negative 0.1, 0.44, and 0.33. Our guess is terrible. They aren't even close. But notice something else. Look closer at the output for the prediction y hat. See that at the end? It says grad n equals add backward 0. Autograd was watching. The nervous system is active. It's already started building the graph that connects our parameters to our prediction. So, let's recap. We've successfully completed the first step. We made a guess. It's terrible. Our y hat is nowhere near the true y. But that's okay. How do we quantify exactly how wrong we are? This is the backward pass. Step 2 of our loop. If the forward pass was the guess, the backward pass is the post-mortem analysis. We compare our guess to the truth, and then we figure out exactly who to blame. Think of it like tuning a radio. Look at this slide. You've got two knobs. Knob 1 is our weight, W. Knob 2 is our bias, B. The static you're hearing? That's our prediction, y hat. And the clear signal we're trying to find? That's the truth, y. The backward pass is all about figuring out which direction to turn each of those knobs to make the static go away. To do that, we need a single number. A scorecard that tells us, on the whole, how badly our model is doing. This number is called the loss. Now, for what we're doing, which is regression, the most common loss function is the mean squared error, or MSE for short. The name sounds a little complicated, but I promise the idea is really simple. Let's look at the formula on the screen. We see L equals 1 over n times the sum of y hat minus y squared. Let's break that down into plain English. For every prediction we make, first you find the difference. That's y hat minus y. Then you square that difference to make it positive. That's the y hat minus y squared part. And finally, you just take the average of all those squared differences. That's it. Let's translate that directly into code. As you can see, we have our y hat, our guess, and y true, the truth. First, we calculate the error, which is just y hat minus y true. Next, we get the squared error by taking that error to the power of 2. Finally, our loss is just the squared error dot mean. Now let's print it out. Print loss. Our single scorecard number is loss. And here's our scorecard. The loss is 1.6322 and so on. Now here's the thing. The number 1.63 doesn't mean much on its own. All that matters is that our goal is now crystal clear. Make this number as small as possible. And notice, This loss tensor also has a grad stance. It knows it's the result of all the previous calculations. It sits at the very end of our computation graph. It is the source from which all knowledge will flow backward. Now for the magic. How do we know which way to turn the W and B knobs to lower that score? This is where Autograd does all the heavy lifting for us, with one single command. In fact, this might be the single most powerful line of code in all of PyTorch. We are telling PyTorch, travel backward from the loss, and calculate gradients for all parameters that have requires grad equals true. In our case, it will compute the two most important values we need. First, the partial derivative of L with respect to W. In other words, the gradient of the loss with respect to our weight W. And second, the partial derivative of L with respect to B, the gradient of the loss with respect to our bias B. Ready? Here is the command. Loss.backward. That's it. No output. It looks like nothing happened. So, what just happened? PyTorch just performed the most critical step of the learning process. It populated a hidden attribute for our W and B tensors, the .grad attribute. Let's inspect the result. The gradient is the answer. The .grad attribute now holds the signal that tells us exactly how to adjust our knobs. As you can see in the code, first we compute the gradients by calling loss.backward. Then we can just print them. Let's print the gradient for W and the gradient for B. And here they are, the directions. The gradient for W is a tensor with negative 1.0185. And the gradient for B is a tensor with negative 2.0673. This is the aha moment. What do these numbers actually mean? Look at W.grad. It's negative 1.0185. The sign is everything. A negative gradient means that if we were to increase W, the loss would decrease. The gradient always points toward the steepest increase. So to minimize the loss, we need to go in the opposite direction. Now look at B.grad. It's negative 2.0673. It's the same story. A negative sign means increasing B will decrease the loss. And the larger magnitude just means the slope is a little steeper for B right now. So there we have it. We have what we need to improve. We can measure our error using the loss. And we know the exact direction to go thanks to the .grad attribute. The postmortem analysis is complete. The blame has been assigned. The final step is to actually act on this information. Let's use an analogy. Imagine we are standing on a foggy mountain. We can't see the bottom, but we want to get there. The loss tells us our current altitude. The higher the loss, the higher up we are. The gradients, which we just calculated in the last chapter, they tell us the direction of the steepest slope. So what do? We take a small step downhill. And we do it again, and again, and again. This is it. The heart of the entire deep learning process. The training loop. This is where learning actually happens, through a simple and beautiful algorithm called gradient descent. This brings us to the single most important formula in all of deep learning. Let's look at it. Theta at time t plus 1 equals theta at time t minus eta times the gradient of L with respect to theta. Now that looks complicated, but it's actually super simple once you break it down. Okay, let's translate that. First, theta. That represents all our parameters. For us, that's just W and B. Next, eta. That's the learning rate. It's just a small number, maybe 0.01, that controls our step size. It's how big of a step we take downhill. And finally, the gradient of the loss. We just calculated this. It's the information waiting for us in w.grad and b.grad. So the update rules in our code become a direct translation. W new equals W old minus the learning rate times w.grad, and B new equals B old minus the learning rate times b.grad. That's it. We are literally just nudging our parameters in the opposite direction of the gradient. Let's put it all together into the training loop. We just repeat our 5 steps for multiple epochs. An epoch is just one full cycle through our learning process. Now, there are 2 new and critical details here. First, you'll see a block that says torch.nograd. This tells PyTorch, hey, don't track these parameter updates in your computation graph. I'm doing this manually. And second, you'll see .grad.0_. This is so important. It resets the gradients after each iteration. If we didn't do this, the new gradients would just add on to the old ones, and we'd get completely lost on our foggy mountain. Here is the entire training process in one beautiful block of code. We'll walk through this step by step. First, we set our hyperparameters, a learning rate and the number of epochs. Then, we reinitialize our parameters W and B with random values, making sure to set requires grad equals true. Now for the training loop itself. For each epoch, we perform steps 1 and 2. We do our forward pass to make a guess, which is y hat, and then we calculate our error, which is the loss. Next is step 3, the backward pass. We call loss.backward to calculate the blame for the error, in other words, the gradients. And here's the new part. Step 4, we nudge the parameters in the correct direction. This is the gradient descent step, where we subtract a tiny fraction of the gradient from our parameters. And finally, step 5, we reset for the next round of learning. We call .grad.0_ to zero out the gradients and get ready for the next epoch. Now, for the payoff. Let's add a print statement inside that loop and watch what happens. We'll print the epoch number, the loss, W, and B every 10 epochs so we can see the progress. At the end, we'll print our final learn parameters and compare them to the true parameters we were trying to find, which were a W of 2 and a B of 1. Let's run it. Look at this table. At epoch 0, our loss is a pretty high 4.1451. Our initial random guess for W is way off, at negative 0.347. And B is at 0.505. Now watch. After just 10 epochs, the loss has plummeted to 1.04. W has already become positive. At epoch 20, the loss is down to 0.29. Look at W and B. One is almost at 1, and the other is just over 1. They're getting so much closer. And it just keeps going. Epoch 30, 40, 50. Look at those numbers converge. I'm not going to read all of them, but you can see the trend. The loss keeps dropping, and W and B get closer and closer to the truth. It's incredible. Watch the learning happen. The loss is plummeting. W is marching steadily toward its true value of 2.0, and B is honing in on its true value of 1.0. It works. It actually works. We have successfully implemented the entire gradient descent algorithm from scratch. We have built a machine that learns. We just built a learning machine from scratch. It was amazing. But let's be honest. We had these loose tensors named W and B. We had to manually update them. We had to manually zero their gradients. It was messy. Now, imagine your model has 50 layers, 1,000,000 parameters. Are you going to write 1,000,000 lines of code? Absolutely not. There has to be a better way. This is where we graduate. We go from working with raw clay to building with high-quality, standardized Lego bricks. Welcome to the torch.nn.Module, PyTorch's library of pre-built layers that forms the backbone of every single professional model. Let's talk about the workhorse, torch.nn.Linear. The first Lego brick we'll grab is one that looks very familiar. The torch.nn.Linear layer does exactly what our manual x at w plus b operation did. But instead of leaving w and b as loose tensors floating around, it neatly packages them inside a professional object. Let's look at how to use nn.Linear. We are going to walk through this together, step by step. First, we define our dimensions. d_in equals 1, because our input has one feature. d_out equals 1, because the output has one value. Next, we create the linear layer Lego brick itself. We'll call it linear Lego bricks equals torch.nn.Linear, with in features equals d_in, and out features equals d_out. Now, here's the cool part. You can look inside and see the parameters it created for you. If we print linearLayer.weight and linearLayer.bias, check this out. Look at this output on the slide. The layer's weight, W, is a parameter containing a tensor. And notice it says requires grad equals true. It did that for us. Same for the layer's bias, B. And to use it, you just use it like a function. This is the forward pass. We just call y_nn equals linear layer and pass in our x. And you can see the output of nn.linear right there on the slide. So much cleaner. So what is a parameter? It's a special kind of tensor that 1 has requires grad equals true by default. 2, it auto-registers with the model. And 3, it handles all the bookkeeping for you. No more manual work. Linear models are powerful, but they have a hard limit. If you stack a bunch of linear layers, it's the same as just having one bigger linear layer. They can only ever learn straight lines. To learn the complex, messy patterns of the real world, you need to introduce kinks or nonlinearities between your linear layers. This is the job of an activation function. First up is nn.ReLU. That's ReLU for rectified linear unit. The rule is dead simple. If an input is negative, make it 0. That's it. ReLU of x equals max of 0, x. Look at this example. We create the layer. ReLU equals torch.nn.ReLU. We have some sample data, a tensor with -2, -0.5, 0, 0.5, and 2. And we pass it through the layer. And the output? Look, the original data is on top. The data after ReLU, all the negative values, are just gone. They've been set to 0. Simple and effective. nn.GELU, this is the modern standard for transformers, like GPT and Llama. Think of it as a smoother, gently curving version of ReLU. Let's run the same code. We create the layer, GELU equals torch.nn.GELU. We use the exact same sample data. But now, look at the output. The negative values aren't snapped to 0. They're just gently squashed towards it. This little bit of smoothness can make a huge difference in training massive models. nn.softmax. This one is special. You almost always use it on the final output layer for classification problems. Its job is to convert the raw model scores, which we call logits, into a probability distribution. What does that mean? The output values will all be between 0 and 1, and they will all add up to exactly 1. Let's see nn.softmax in action. We create the layer, softmax equals torch.nn.softmax, and we set dim equals -1. Now, imagine our model gave us some raw logit scores for 2 different items across 4 possible classes. You can see them there in the logits tensor. When we pass that through softmax, look at the output probabilities. For the first item, the highest logit was 3.0. Softmax turned that into the highest probability, 0.6558. And if you sum up the probabilities for that first item, they equal 1.0. Perfect. Pay attention. What we're about to cover isn't just a toy. These are the literal, non-negotiable building blocks of models like GPT, Llama, and Gemini. First up, nn.embedding. This layer's job is to turn words into numbers. It's a giant, learnable lookup table. Each word gets its own unique vector. Let's see it in code. We'll say our vocabulary size is 10, so we have 10 unique words. And our embedding dimension is 3, so we'll represent each word with a 3D vector. We create the layer. Embedding_layer equals torch.nn.embedding with the vocab size and embedding dimension. Now for our input. This is a sentence where each word is an ID. For example, the IDs 1, 5, 0, and 8. When we pass those input IDs to the layer, look at the output word vectors. Our input had a shape of 1 by 4. And our output has a shape of 1 by 4 by 3. For each of our 4 input IDs, it looked up and returned the corresponding 3-dimensional vector. This is the first step in every large language model. Next, nn.layerNorm. As data flows through a deep network, the numbers can explode or vanish, making training impossible. LayerNorm is the traffic cop. It rescales everything to a stable range. This is essential for deep networks. Here's the code. Our word vectors have a feature dimension of 3, so we create a norm layer equals torch.nn.layerNorm with a normalized shape of 3. We create some sample input features. And when we pass them through the layer, look at the results. The mean of each output vector is basically 0. The standard deviation is basically 1. It keeps the network stable. It's beautiful. And finally, nn.dropout. This is a brilliant trick to prevent overfitting. During training, it randomly zeroes out some of the neurons. This forces the network to become more robust and not rely on any single neuron. But here's the most important thing. It only happens during training. Let's look at the code for dropout, comparing train versus eval mode. We create a dropout layer that will zero out 50% of inputs. Then we create an input tensor of all ones. First, we activate dropout for training by calling dropout_layer.train. Look at the output during training. It's randomly zeroed and scaled. Some values are 0, others are 2. Now, we deactivate dropout for evaluation by calling dropoutLayer.eval. And the output? It's the identity function. It just passes the original tensor of all ones straight through. This simple on-off switch is a cornerstone of modern deep learning. Remember this code from our last training loop? The from-scratch way, where we used torch.nograd, then manually updated our weights? W minus equals learning rate times w.grad. Then we did the same for our bias b. And finally, we had to manually zero out the gradients for both w and b. Now, imagine your model has 50 layers, 1,000,000 parameters. Are you really going to write 1,000,000 lines of code to update each parameter? and then zero its gradient? Absolutely not. We need to go pro. PyTorch provides two core Brine to clean all of this up. First, nn.Module, which we use to organize our model. And second, torch.optim, which we use to automate the learning. Think of it this way. nn.Module is the instruction booklet and the baseplate for our Legos. It provides a standard structure for how all your little bricks connect. Then you have torch.optim. This is the skilled builder who knows exactly how to adjust all the bricks according to the instructions from the gradients. So let's do it. Let's refactor to professional PyTorch. Clean, standard, and scalable. First up is the model blueprint, nn.Module. The pattern is always the same. You inherit from torch.nn.Module. You define your layers in the _init method. And you connect the layers in the forward method. That's it. Let's rebuild our model. First, we import torch.nn as nn. Then, we define our class linear regression model. And notice we inherit from nn.Module. Inside the constructor, the init method, we first call super.init. This is super important. Then, we define the layers we'll use. We'll create one, self.linearLayer equals nn.linear with infetcher and outfeatures. Now, in the forward pass, this is where we connect the layers. We just return self.linearLayer applied to our input x. Finally, we instantiate the model. Model equals linear regression model with infiguration equals 1 and outfeatures equals 1. And here's the professional result. When we print the model, look at this beautiful output. It prints the model architecture. Linear regression model, containing a linear list, which is a linear layer with infeatures equals 1, outfeatures equals 1, and bias equals true. All our parameters are now neatly organized. No more loose tensors. Whew. Next up, the optimizer, torch.optim. We're going to replace our manual weight update. And the most common optimizer, the one you should almost always start with, is Atom. We import torch.optim as optim. We set our hyperparameter, learning rate, equals 0.01. Then we create the optimizer. Optimizer equals optim.atom. And here's the key part. We pass model.parameters to tell it which tensors to manage. We also pass our learning rate. And while we're at it, let's grab a pre-built loss function from torch.nn. We'll use loss.fx equals nn.mse loss. The stage is set. We have our organized model and our automated builder. We are about to rewrite our training loop. What was once 5 messy manual steps will become an elegant, high-level process. This is the universal pattern you will see in 99% of all PyTorch code. It all boils down to what I call the 3-line mantra. Number 1, optimizer.0_twiddled line. Number 2, loss.backward. Number 3, optimizer.step. That's it. That's the entire engine. Let's compare the from-scratch loop versus the professional loop. On the left, our old way. On the right, the new way. Step 1, the forward pass. Before, it was y hat equals x at w plus b. Now, it's just y hat equals model x. So much cleaner. Step 2, loss calculation. Before, we wrote out the whole mean-squared error formula. Now, we just call loss equals loss_fn of y hat and y true. And now for the big one, steps 3, 4, and 5. Before, we had 3 separate manual steps, loss.backward, then updating w and b by hand, then zeroing out their gradients. Now, it's all replaced by the 3-line mantra. optimizer.zeroGrad, loss.backward, optimizer.step. So much better. Let's look at the final clean training loop. We set our epochs to 100. We start our for loop. First, the forward pass. Y hat equals model X. Next, we calculate the loss. Loss equals loss GTK with our predictions and true values. And now, the three-line mantra. 1. Zero the gradients. Optimizer.zeroGrad. 2. Compute the gradients. Loss.backward. And 3. Update the parameters. Optimizer.step. And that's it. We can add an optional print statement to watch our progress. And look at that. The same beautiful result. Epoch 0. The loss is 2.6515. By epoch 10, it's 1.7. By epoch 50, it's down to 0.0886. And by epoch 90, the loss is down to 0.0210. Perfect. We achieved the exact same outcome. But our code is now organized, scalable, and uses the STRED-optimized tools that power real-world AI. You might be sitting there thinking, this is great for a toy model that learns a straight line. But how does any of this relate to a massive LLM like GPT? And this is the final, most important lesson of this entire hour. It is not an analogy. You have learned the exact fundamental components and the universal process used to train them. You see, the difference between our tiny model and an LLM is not one of kind. It is one of scale and architecture. So let's make the direct link. Let's look inside the transformer's feed-forward network. Inside every single transformer block, and that's the architecture behind all modern LLMs, there's a little subcomponent called a feed-forward network, or FFN. And if we look at the code for it, here it is. This is the literal PyTorch code for an FFN. And here's the amazing part. Look at that code. You can read this perfectly. It's a class called feed-forward-network that inherits from nn.Module, just like ours did. And what's inside? The Lego bricks we already know. There's self.layer1 equals nn.linear. There's an activation function, in this case, nn.gelu. And then there's self.layer2, which is another nn.linear. The forward method is exactly what you'd expect. The data goes through layer 1, then the activation, then layer 2. That's it. The feed-forward network inside a multi-billion parameter model is literally this simple. The model's incredible power comes from stacking dozens of these blocks, and each of those blocks contains one of these FFNs and a self-attention mechanism, which itself is also built from nn.linear layers. So let's get a real sense of scale. Check out this table. We're going to compare our toy model to a typical LLM like Llama 3 8B. First row, the model. For us, it was our linear regression model. For the LLM, it's a transformer. Makes sense. Second row, the layer. For us, we used nn.linear. For the LLM, inside one of those FFNs, it's also nn.linear. Now, here's where it gets wild. Look at the weight matrix W shape. For our toy model, the shape was 1 by 1. A single number. For just one of the linear layers in the LLM's FFN, the shape might be 4096 by 14,336. That's over 58 million values in a single matrix. But the operation, matrix multiplication, it's the same. X at W for us, X at W for the LLM. And finally, total parameters. Our toy model had 2. The LLM, around 8 billion. And this is the most important part. The process we used to train our 2-parameter model is the exact same process used to train that 8 billion parameter LLM. The 5-step logic is universal. Let's break it down. Step 1. Y hat equals model of X. For us, that model was a single linear layer. For the LLM, it's dozens of transformers. But the call is the same. Step 2. Loss equals loss underscore fn. For us, we used mean squared error. The LLM uses something called cross-entropy loss to predict the next word. The goal is different, but the concept is identical. Get one number that represents the error. Now for the last 3. Optimizer.0med. For the LLM, identical. Loss.backward. For the LLM, identical. Autograd doesn't care how deep the model is. Optimizer.step. For the LLM, you guessed it, identical. The optimizer just does its job, whether it's managing 2 parameters or 8 billion. You've done it. In this hour, we have journeyed from a single number in a tensor to understanding the engine that powers the largest AI models in the world. The magic of deep learning is gone. It has been replaced by engineering. You now know that a model is just an NN.Module containing layers. A layer is just a container for parameters that performs a mathematical operation. And learning is just updating those parameters with zero grad, backward, and step. You now understand the engine. You are ready to move on from how a model learns to what a model learns, with a rock-solid foundation in the principles that bring it all to life.